Hi everyone, I'm Shu-Bo. I'm from Department of Chemical and Materials Engineering from University of Alberta. Today I'm going to introduce my research, which is the data-driven process optimization under neural network stable model uncertainty. I'm glad to have this presentation at 2020 virtual AIChE annual meeting. Here's the outline of the presentation. First, I will give you a brief introduction about segment model-based optimization, which is an efficient way to deal with the optimization problem with complicated model embedded. And then I will show you the segment model prediction uncertainty, which is because segment models are usually data-driven models, so they are highly influenced by the training data set variation. And then I will illustrate the methods for handling prediction uncertainty. After that, I will show you the mixture density network-based optimization approach, which is the main approach in our research. And then I will show you the applications of the proposed approach to an illustrating example and one case study, which is the optimization of a distillation column process. At the end, I will conclude all the advantages about the proposed approach. Let's consider why we use segment model-based optimization. First, let's consider the optimization with the model embedded. In this optimization, a complicated chemical process model is incorporated in the optimization formulation to compute f of x and g of x. In this optimization, we want to minimize f of x subject to g of x less or equal to 0. Because this embedded model is very expensive to compute, so if we want to optimize the whole problem with several times with different parameters and different specifications, that would be very time consuming and not so efficient. So another way to deal with this problem is to use segment model to approximate the forward model here to make it more efficient. So it is called a segment model optimization. First, we use segment model to approximate the forward model. And because the f of x and g of x output from the forward model are approximated by the segment model here, which are the f of 8 and g of 8. And again, we want to minimize f of 8 and subject to g of 8 this equal to 0. So it is called the optimization with segment model embedded and also the segment model-based optimization. It is a very efficient way to make the original optimization problem to be more efficient and to be more time-saving. The segment model we use in this research is called the ReLU-ANN, the ReLU Artificial Neural Network. This segment model has strong approximation ability to approximate the nonlinear model. Also, it can be formulated as MIP formulation. All the outputs of the nodes in this ReLU-ANN can be expressed as this equation here, and the activation function we use in this segment model is called the ReLU activation function. So this is why this segment model called the ReLU artificial neural network. The activation function of y can be illustrated by this figure here. If y is less or equal to 0, the output of the activation function equal to 0. Otherwise, it equal to y itself. And the whole ReLU artificial neural network can be expressed as the equations here. The first equation means the input layer of the ReLU artificial neural network, and the equations here means the hidden layers inside the ReLU artificial neural network. And the last equation expresses the output layer of the ReLU artificial neural network. Although the ReLU artificial network is a very powerful segment model, however, it is also a data-driven method that it is highly influenced by the data variation. So it may cause the prediction uncertainty. The prediction uncertainty originates from the training data set variation, and the training data set variation usually caused by the randomness of the data collection. Let me illustrate this idea by the following example. First, we want to sample 100 times from the forward model to get 100 different training sets. And then we use these 100 different sets to train 100 different neural networks. If we input one observation into those 100 neural networks, we get 100 sets of predictions. We can call it the prediction uncertainty originates from the 100 different training sets, originates from the randomness of the data collection. There are several methods for addressing prediction uncertainty from literatures. However, these methods from literatures are not feasible to deal with prediction uncertainty in an optimization framework because the first four methods are too complicated to be compiled in an optimization framework, and that's why it's too time consuming to deal with the prediction uncertainty in an optimization framework. So in our research, we use a more straightforward way, which is called the mixture density network, to deal with the prediction uncertainty in an optimization framework. How we use mixture density network, which is the MDN, to deal with the prediction uncertainty in an optimization, let me illustrate with the following example. First, we sample 100 times from the forward model to get 100 different training sets to train 100 different neural networks. If we input one observation into those 100 neural networks, we get 100 sets of predictions, and then we can get corresponding means, standard deviation of the predictions. If we plug multiple inputs into the 100 neural networks, we get multiple prediction means and standard deviations as targets, paired with corresponding decision variables as inputs. Use these targets and inputs to train the mixture density network. And the mixture density network is exactly the same as the traditional neural network. The structure, the mathematical formulation are all the same as the traditional neural network. The only difference is that the output of the mixture density network are the parameters for constructing the prediction distribution. Because of the training set for the mixture density network used means and standard deviation of prediction as targets. After that, we can embed the whole MDM model into the optimization framework, and then we reformulate the objective function of the original problem to be the inference type objective to deal with the solution quality and solution variability subject to a change constraint here. The change constraints ensure that the original I mean to ensure that the original constraints to be satisfied with the probability greater or equal to an user-defined constant level, and these change constraints can be reformulated equivalently as this linear form. As you can see, the -1 over psi here means the inverse cumulative distribution function, and the distribution in this research is assumed to be Gaussian distribution here, and the feasibility of Gaussian assumption is shown in page 16, and you can find the slides in my iPoster. And then I apply the proposed approach to an illustration example, and this illustration example is a numerical, simple, nonlinear, non-convex optimization problem. And the global solution and local solution are already known in this illustrated example. How I use the proposed approach to deal with this illustrated example. First, I sample around 50,000 sets of F, G1, G2 with corresponding X and Y as the data set. And then I generate 100 different training sets. Each training set composed of around 44,000 samples, and each sample is resampled from the 50,000 sample sets I got from the previous step by using bootstrap method. And then I can train 100 different neural networks, the radio neural networks separately with 100 different training sets. And then I can plug numerous observations into these 100 neural networks to get around 50,000 sets of prediction means and standard deviations. And those 50,000 prediction means and standard deviations can be paired with 50,000 corresponding inputs as the training data set to train the MDM. And one remark here is that all the MDM and radio IELU-AN in this research individually have two hidden layers with 50 and 30 neurons for the first hidden layer and second hidden layer respectively. And then we can incorporate the trap median into the optimization framework here. And as you can see from the optimization framework here, the variables in blue boxes are computed from the incorporated MDM, and the parameters in the red boxes are user-defined parameters, And then we can solve this optimization several times with different user-defined parameters. And we can obtain several different optimal solutions, as we can see from these figures. From this figure, if I increase lambda and confidence level, we get more robust optimal solution with higher constraint satisfaction probability. If we want our confidence level to be 0.99, we get a solution with constraint satisfaction probability higher than 0.99, which means that this proposed approach is reliable to deal with the illustrative example in this case study. After that, I applied the proposed approach to another case study, which is the minimization of the total annual cost of an ethanol water separation distillation column. And we want the ethanol mole fraction at the top to be greater or equal to 0.8, ethanol recovery at top to be greater or equal to 0.9, with the following decision variables. The decision variables are reflux ratio, reborn duty, total stage number, and feed stage number. And those equations are simple bounds for decision variables. And again, we sample from the folder model first. We sample 120,000 sets of total annual cost, mole fraction, recovery at targets, paired with corresponding reflux ratio, reborn duty, number of stage, and feed stage number as observations. And then we generate 120 sets. Each 20 sets includes 100,000 samples, and each sample resample from the 120 sample data set I just got from previous step by using bootstrap method. After that, I can train 100 neural networks, the 100 value ANNs, based on 100 different training sets I got from the previous step. And then I can plug 120 inputs into the train 100 ReLU ANNs to get 120,000 prediction means and standard deviations paired with 120,000 inputs to train the MDN. And then I can incorporate the MDN into the optimization framework here, and to solve the optimization several times with different user-defined parameters like confidence level and lambda. After that, we got several optimal solutions with different constraint satisfaction probability. As I increase lambda and confidence level, we got a solution with higher constraint satisfaction probability. And if we want the confidence level to be greater or equal to 0.99, we got a solution with constraint satisfaction probability higher than 0.99, which means that this proposed approach is reliable for dealing with this more complicated case study. And as you can see from the obtained results in this table, an important information is that the solution time of the MDM-based optimization is only 89 seconds, which is much less than the solution time it takes from the folder model optimization. It means that the MDM-based optimization can not only get robust optimal solution, it can get a solution with this solution time than the folder model optimization, which means that the MDM-based optimization is more robust and more efficient than the folder model optimization. So finally, let's go to the conclusion. The MDN is employed to address the single model prediction uncertainty in an optimization framework in this research. And then the proposed MDN-based optimization can be easily programmed as a MIP problem, and it can be solved by common solver like C+ in games. And then the proposed approach can achieve robust optimal solution under prediction uncertainty. Finally, the obtained solution robustness can be adjusted via tuning user-defined parameters like lambda and confidence level. So based on this conclusion, we can say that this proposed MDM-based optimization approach is very reliable to get robust optimal solution with reasonable solution time, and it is much more efficient than the folder model optimization. So thank you for your attention, and I gratefully acknowledge the financial support from the Natural Science Engineering Research Council of Canada for this research. That's all about today. Thank you for your attention again.